Oh, hello everybody. Nice to see everybody again. Today, what we're going to be looking at is the concept of 95% confidence intervals, which in epidemiology is probably one of the most difficult concepts, and it's one that a lot of students struggle to understand properly. So hopefully we're going to go through what it all means and try and give you a bit of an understanding of where 95% confidence intervals come from, because they are very important. Okay, I'm just going to use this little chart here to help with the description. On this axis here is just what we call frequency, and here I'm looking at the height of women in Liverpool. We're here in Liverpool, so we're going to look at the height of women. And now if I went out and I measured the height of all the women in Liverpool, I would end up with something that looks a bit like this. I would take the heights, and there'll be very few women here. This is frequency, remember. So there'll be very few women here who are very short. And there'll be a few women here who are very tall. Most of the women will be somewhere in the middle. All right? And this is what we call a normal distribution. And in this case, it's the same on both sides. And the bit in the middle is what we call the mean or the average, and that's right in the middle, and it's at the highest point. So most people are average, some people are a bit taller than average, some people are a bit shorter. One of the properties, and this is the beautiful thing about the statistics in epidemiology, one of the wonderful things about a normal distribution is that we know that if we can calculate one standard deviation away from the mean, so I've roughly put it in here, from here to there, we know that approximately 68% of the population will be within that range there, somewhere. Okay. If we can calculate two standard deviations away from the mean, we know that there will be 95% of the population is between there and there. Actually, it's not exactly 2, it's actually 1.96, but I'm using 2 just to make it simple. All right? Okay, so that's the first thing to remember. And that's a property of any normal distribution. So it doesn't matter what it's looking at, this is what we know, is 68% are within one standard deviation, and 95% are within 2, if we look at either side. That means approximately 5% of the population are either side here, 2.5% there, 2.5% there. Okay, fine. Right, so this is looking at all the women in Liverpool. Of course, if I really wanted to measure the heights of women in Liverpool, I can't go and measure the heights of everybody. It's practically impossible. So what I do is I'll take a sample. Okay. Right, so I've got my sample. And let's say that for the first time I'm going to take a sample of just 30 people, 30 women. So I'll go out onto the streets of Liverpool and I'll take a sample of 30 women. So I will then find the average of this sample, and most likely it will be on this continuation here, because don't forget, this is the shortest woman in Liverpool, this is the tallest woman in Liverpool. If I've taken a good random sample, most likely the mean from my sample, it will be somewhere along here. It could be here or here. All right? Okay? Fine. Now, let's just say on this particular day, I go out and take my sample. And by sheer bad luck, I take a sample of the shortest women in Liverpool. These are 30 of the shortest women in Liverpool. The question is, where along this continuum, I take the average of those shortest women, where will it be? This is the question. It can't be here, because that there represents the shortest woman in Liverpool. Right? It must be somewhere over here. All right? Maybe it'll be about there. Okay? So that's my 30 shortest women in Liverpool. Okay, and again, okay, this isn't a very good sample, so I go out and take another sample, and then by sheer bad luck, I get the 30 tallest women in Liverpool. Again, where will it be? On this, it'll be somewhere on here, because that's the tallest and that's the shortest. Because they're the 30 tallest, it can't be beyond the very tallest woman. So it will be within here somewhere, probably somewhere around there. Okay? Right. So I've got these two extremes. All right. These are not very good. Yeah. Right. So what about now, instead of taking the 30 women, let's say I take 100 women. Right? And again, if I take 100 women, rather than, most of the time my samples will be around here somewhere. Okay? But if I take, again, just by sheer chance, I happen to get 100 of the shortest women in Liverpool, where will that be along here? Obviously it can't be beyond here, that's the shortest. This is the 30 shortest. If I've got 100 short women, it will be to this side somewhere. It can't be beyond there. So it will be somewhere around here maybe. And the same if I happen to take the 100 tallest women. So can you see what's happening here? Is that essentially as my sample size is increasing, in a way my accuracy is getting better. Okay? All right? Now let's say I took lots, instead of taking just one sample, which is what we would normally do, let's take, I take lots and lots and lots and lots and lots and lots of samples of size 30. That will be my shortest there. That will be my tallest there. And if I plotted all of those, I would end up with something that looked a bit like this. And as you can see, it's another normal distribution. And actually, the mean of that would be the true mean. This is the true mean, the green one. So the mean of my sample, if I took lots and lots and lots of size 30, it would be like that. If I took lots and lots and lots and lots of size 100, samples of 100, obviously it would start further in. Oh, sorry, and it would come up and it would be probably taller in the middle. It would look more like that. So again, it would be another normal distribution. The true mean, the mean of the sampling distribution would be the true mean. Okay. Sorry, it's beginning to look a bit messy here now. I've got lots of different normal distributions. But the point is that we've got here, this is all of the women in Liverpool. But remember, this is when I've taken a sample of size 30. All right? It will be, every time I do it, it will be nearer to even if I take the 30 shortest women, it will be nearer to the true population mean. Right? And the same here. The shape of this sampling distribution, as my sample size increases, it gets narrower and it gets taller. All right? Now, why does that matter? Well, why that matters is, if you remember what we said, these are still normal distributions. All right? And we know that if we can work out the two standard deviations, all right, we know that 95% of those sample means will be within two standard deviations of here. So it will be something like that from there to there. Okay? All right. And don't forget that's the true population mean there. All right. So you see, the thing is, in reality, of course, we don't take lots and lots and lots and lots of different samples. We normally just take one and hope that that's good enough.